Now that we understand how DES works, let's look at a few attacks on DES, and we're going to start with an attack called Exhaustive Search. So our goal here is basically that given a few input-output pairs, MI-CI, our goal is to find the key that maps these M's to the C's. In other words, our goal is to find the key that maps M1, M2, M3 into C1, C2, C3. And as I said, our goal is to find the key that does this mapping. The first question is, how do we know that this key is unique? And so let's do a little bit of analysis to show that, in fact, just one pair is enough to completely constrain a DES key, and that's why this question makes sense. Okay, so let's see. So we're going to prove this simple lemma. Now let's assume that DES is what's called an ideal cipher. So what is an ideal cipher? Basically, we're going to pretend like DES is made up of random invertible functions. In other words, for every key, DES implements a random invertible function. Since there are 2 to the 56 keys in DES, we're going to pretend like DES really is a collection of 2 to the 56 functions that are invertible from 0, 1, 64 to 0, 1, 64. Okay, so of course DES is not a collection of 2 to the 56 random functions, but we can idealize the cipher and pretend that it is such a collection. Then what can we say? Then, in fact, it turns out that just given one message and ciphertext, you just give me one pair, message and ciphertext, there's already only one key that maps this message to that ciphertext. So already, just given one pair, M and C, I can ask you, find me the key that maps M to C, and the solution is very likely to be unique. In fact, it's going to be unique with probability roughly 99.5%. I should say that this statement is true for all M and C, and the probability is just over the choice of the random permutation that make up the cipher. So let's do the proof. This is fairly straightforward. So what we're basically asking is, what's the probability that there exists some key that's not equal to K, such that, well, C we know is equal to DES of K comma M, by definition of C and M, but we're asking how likely is it that there's this other key K prime that also satisfies this equality. You realize that if this is true, if such a key K prime exists, then just given M and C, you can't decide whether the right key is K or K prime, because both of them work. Okay? But I want to argue that this happens with low probability. Well, so what does it mean that there exists a key K prime that satisfies this relation? Well, we're asking, what's the probability that the first key, the all0 key satisfies it, or the second key satisfies it, or the third key satisfies it, and so on and so forth. So by the union bound, we can bound this probability by the sum over all keys K prime, over all 56-bit keys, of the probability that des Km is equal to des K prime M. Okay, so we're asking basically, what is this probability for a fixed key K prime that it happens to collide with the key K at the message M? Well, let's think about this for a second. Let's fix this value. Let's suppose it's some fixed value. And then we're asking, how likely is it that a random permutation pi K prime at the point M happens to produce exactly the same output as the key K at the point M? Well, it's not difficult to answer and see that in fact this is, for a single key K prime, the probability is at most 1 over 2 to the 64. Right? There are 2 to the 64 possible outputs for the permutation. What's the probability that it lands exactly on this output? Well, it's 1 over 2 to the 64. And we're summing over all 2 to the 56 keys. So we just multiply the 2. We get 1 over 2 to the 8, which is basically 1 over 256. Okay? So the probability that the key is not unique is 1 over 256. Therefore, the probability that it is unique is 1 minus that, which is 99.5%. Okay, so already, if you give me one plain text ciphertext pair, the key is completely determined. There's only one key that will map that plain text to that ciphertext, and the question is just, can you find that key? Now, it turns out, in fact, if you give me two pairs, so you give me M1 and M2, and their corresponding outputs, C1 and C2, the probability, basically, just do exactly the same analysis, the probability basically becomes 1, that there's only one such key. Okay, essentially, this is very, 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 very close to 1, and basically it says given two pairs, it's very, very likely that only one key will map this pair of messages to this pair of ciphertexts, and as a result, again, we can ask, well, find me that unique key. And by the way, the same is true for AES. If you look at AES 128, again, just given two input-output pairs, there's going to be only one key with very high probability. So essentially now we can ask for this exhaustive search problem. I give you 2 or 3 pairs, and I ask you, well, find me the key. So how are you going to do it? Well, you're going to do it by exhaustive search, essentially by trying all possible keys one by one until you find the right one. So this is what's known as the DES challenge. So let me explain how the DES challenge worked. The challenge was issued by a company called RSA. And what they did is basically they published a number of ciphertexts, but 3 of the ciphertexts had known plaintexts. So in particular, what they did is they took the message here, the unknown message is colon, and you can see they broke it up into blocks. If you look at these are basically 8-byte blocks. 8 bytes, as you know, is 64 bits. Right? So each one of these is 64 bits. And then they encrypted them using a secret key. They encrypted all using the same secret key to get kind of 3 ciphertexts. So this gives us 3 plaintext ciphertext pairs. And then they gave us a whole bunch of other ciphertexts, C4, C5, C6. And the challenge was decrypt these guys using the key that you found from an exhaustive search over the first 3 pairs that you were given. Okay. So that was called the DES challenge. And let me tell you a little bit about how long it took to solve it. So interestingly, in 1997, using an internet search, using distributed.net basically, they were able to search through enough of the key space to find the correct key in about 3 months. You realize the key space has size 2 to the 56, but on average you only have to search through half the key space to find the key, and so it took them 3 months. Then kind of a miraculous thing happened. The EFF actually contracted Paul Kocher to build special purpose hardware to break DES. This was a machine called DeepCrack. It cost about $250,000, and it broke the next DES challenge in only 3 days. Interestingly, by the way, RSA said that they would pay $10,000 for each solution of the challenge, so you can see that this is not quite economical. They spent $250K, they got $10,000 for solving the challenge. The next thing that happened is in 1999, RSA issued another challenge, and they said, well, you got to solve it in half the time of the previous solution. And so using both DeepCrack and the internet search together, they were able to break DES in 22 hours. So the bottom line here is essentially DES is completely dead. Essentially, if you forget or you lose your DES 56-bit key, don't worry. Within 22 hours, you can actually recover it. And in fact, anyone can recover it. And so DES essentially is dead and no longer secure. And just kind of a final nail in the coffin, as hardware technology improved, there was another project called Copacabana. They used FPGAs, just off-the-shelf FPGAs, only 120 FPGAs. It only cost $10,000, and they were able to do an exhaustive key search in about 7 days. So very, very cheap hardware, just off the shelf. You can break DES already very quickly. So the lesson from all this is essentially 56-bit ciphers are totally, totally dead. And so the question is what to do. People really liked DES. It was deployed in a lot of places. There were a lot of implementations. There was a lot of hardware support for it. So the question was what to do. And so the first thing that came to mind is, well, maybe we can take DES and we can kind of artificially expand the key size so we strengthen it against this exhaustive search attack. And the first idea that comes to mind is basically, well, let's iterate the block cipher a couple of times. And this is what's called triple DES. So triple DES is a general construction. Basically, it says the following. Suppose you give me a block cipher E. So here, it has a key space K, and it has a message space M, and an output space, of course, M as well. Let's define the triple construction, which now uses 3 keys. And it's defined as follows. Basically, here, the triple construction uses 3 independent keys, encrypts the same message block as before, and what it does is it will encrypt using the key K3, then it will decrypt using the key K2, and then it will encrypt again using the key K1. Okay, so it's basically encrypting 3 times using 3 independent keys. You might be wondering, why is it doing EDE? Why not just do EEE? Why do we have to have a D in the middle? Well, that's just for kind of a hack. You notice what happens if you set up K1 equals K2 equals K3? What happens if all 3 keys are the same? Well, basically, what would happen is one E and one D would cancel, and you would just get normal DES out. So it's just a hack so that if you have a hardware implementation of triple DES, you can set all 3 keys to be the same, and you'll get a hardware implementation of single DES. Of course, it'll be 3 times as slow as a regular implementation of single DES, but nevertheless, it's still an option. Okay, so for triple DES, in fact, now we get a key size that's 3 times 56, which is 168 bits. So this is 168 bits is way too long to actually do exhaustive search on. That will take time 2 to the 168, which is more than all the machines on Earth working for 10 years would be able to do. Unfortunately, of course, the cipher is 3 times slower than DES. So this is a real problem with triple DES. Now, I want to mention that, in fact, you might think that triple DES has security 2 to the 168, but in fact, there is a simple attack that actually runs in time 2 to the 118, and I want to show you how that attack works. Okay, so, but in fact, 2 to the 118 is still a large number. In fact, anything that's kind of bigger than 2 to the 90 is considered sufficiently secure. 2 to the 118 is definitely sufficiently secure against exhaustive search, and generally is considered a high enough level of security. So clearly, triple DES is 3 times as slow as DES. So the question is, why did they repeat the cipher 3 times? Why not repeat the cipher just 2 times? Or in particular, the question is, what's wrong with double DES? So here we have double DES. Basically, you see it uses only 2 keys, and it uses only 2 applications of the block cipher. And as a result, it's only going to be twice as slow as DES, not 3 times as slow as DES. Well, the key length for double DES is 2 times 56, which is 112 bits. And in fact, doing exhaustive search on a space of 112 bits is too much. 2 to the 112 is too big of a number to do exhaustive search over such a large space. So the question is, what's wrong with this construction? Well, it turns out this construction is completely insecure, and I want to show you an attack. So suppose I'm given a bunch of inputs, say M1 to M10, and I'm given the corresponding outputs C1 to C10. What's my goal? Well, my goal is basically to find keys, a pair of keys K1, K2, such that if I encrypt the message, the message capital M using these keys, in other words, if I do this encryption, this double DES encryption, then I get the ciphertext vector that was given to me. Okay, so our goal is to solve this equation here. Now you stare at this equation a little bit and you realize, hey, wait a minute, I can rewrite it in kind of an interesting way. I can apply the decryption algorithm, and then what I'll get is that I'm really looking for keys K1, K2 that satisfy this equation here, where basically all I did is I applied the decryption algorithm using K1 to both sides. Okay, now whenever you see an equation like this, what just happened here is that we separated our variables into 2 sides. The variables now appear on independent sides of the equation, and that usually means that there is a faster attack than exhaustive search. And in fact, this attack is called a meet in the middle attack, where really the meet in the middle is going to somehow attack this particular point in the construction. Okay, so we're going to try and find a key that maps M to a particular value here and maps C to the same value. Okay, so let me show you how the attack works. So the first thing we're going to do is we're going to build a table. Here, let me clear up some space here. The first step is to build a table that for all possible values of K2 encrypts M under that value. Okay, so here we have this table. So you notice these are all, I'll say it like this, these are all 2 to the 56 DES keys, single DES keys. Okay, so the table has 2 to the 56 entries. And what we do is basically for each entry, we compute the encryption of M under the appropriate key. So this is the encryption of M under the all 0 key, the encryption of M under the 1 key, and then at the bottom, we have the encryption of M under the all 1 key. Okay, so there are 2 to the 56 entries, and we sort this table based on the second column. Okay, so far so good. So by the way, this takes time to build this table, takes time 2 to the 56, and I guess we also want to sort. Sorting takes n log n time, so it's 2 to the 56 times log 2 to the 56. Okay, so now that we have this table, we've essentially built all possible values in the forward direction for this point. Now what we're going to do is this meet in the middle attack, where now we try to go in the reverse direction with all possible keys K. Essentially, we compute the decryption of C under all possible keys K1. Okay, so now for each potential decryption, remember the table holds all possible values in the midpoint. So then for each possible decryption, we check, hey, is the decryption in the table, in the second column in the table? If it is in the table, then aha, we found a match. And then what do we know? we know that essentially, well, we found a match. So we know that, say, for example, a decryption using a particular key K1 happened to match this entry in the table, K sub 2 or more generally Ki, then we know that the encryption of M under Ki is equal to the decryption of C under K. Okay, so we kind of build this meet in the middle where the two sides, the encryption of M under Ki and the decryption of C under K collided. But if they collided, then we know that in fact this pair, Ki and K, is equal to the pair that we're looking for. And so we've just solved our challenge. So now let's look at what's the running time of this. Well, we had to build a table and then sort it. And then for all possible decryptions, we had to do a search through the table. So there were 2 to the 56 possible decryption. Each search in a sorted table takes log of 2 to the 56 time. If you just work it out, this turns out to be 2 to the 63, which is way, 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 way smaller than 2 to the 112. Okay, so this is a serious attack. It's probably doable today. That runs in a total time of 2 to the 63, which is about the same time as the exhaustive search attack on DES. So really, double DES really didn't solve the exhaustive search problem because, well, there's an attack on it that runs in about the same time as exhaustive search on single DES. Now, someone might complain that in fact this algorithm, well, we have to store this big table, so it takes up a lot of space, but, so be it. That's nevertheless, the running time is still quite smaller, significantly smaller than 2 to the 112. Now you notice, by the way, the same attack applies to triple DES. What you would do is you would implement a man-in-the-middle attack against this point. You would build a table of size 2 to the 56 of all possible encryptions of M, and then you would try to decrypt with all 2 to the 112 keys until you find a collision, and when you find a collision, you've basically found K1, K2, K3. Okay, so even triple DES has an attack that basically explores only 2 to the 112 possible keys. But 2 to the 112 is a large enough number, so triple DES, in fact, as far as we know, is sufficiently secure. I should mention that triple DES is actually a NIST standard, and so triple DES is actually used quite a bit, and in fact, DES should never, ever, ever be used. If for some reason you're forced to use some version of DES, use triple DES, not DES. Okay, I want to mention one more method for strengthening DES against exhaustive search attacks. This method actually is not standardized by NIST because it doesn't defend against more subtle attacks on DES. But nevertheless, if all you're worried about is exhaustive search and you don't want to pay the performance penalties of triple DES, then this is an interesting idea. So let me show you how it works. So let E be a block cipher that operates on n-bit blocks. We're going to define the EX construction, and for DES we're going to get DESX to be the following. So we use 3 keys, K1, K2, K3. And then basically before encryption, we XOR with K3. Then we encrypt using K2. And then after encryption, we XOR with K1. That's it. That's the whole construction. So basically, you notice it doesn't slow the block cipher much because all we did is we applied the cipher plus 2 additional XORs, which are super fast. The key length for this is in fact, we got 2 keys that are as long as the block size. And we got 1 key that's as long as the key size, so the total is 184 bits. Now, it turns out actually the best attack that's known is actually an attack that takes time 2 to the 120, and it's actually fairly simple. So it's a generic attack on EX. It will always take time, basically the block size plus the key size, and it's a simple homework problem for you to try to figure out this attack. I think this is a good exercise. Okay, in fact, there's some analysis to show that there is no exhaustive search attack on this type of construction. So it's a fine construction against exhaustive search, but there are more subtle attacks on DES that we'll talk about in the next segment that basically this construction will not prevent. One thing that I want to point out, unfortunately I found this mistake in a number of products, is if you just decide to XOR on the outside, or if you just decide to XOR on the inside, as opposed to XORing on both sides, which is what DESX does. You notice DESX XORs both on the outside and on the inside. If you just do one of them, then basically this construction does nothing to secure your cipher. It'll still be as vulnerable to exhaustive search as the original block cipher E. Okay, so this is another homework problem, and actually you'll see that as part of our homeworks. Okay, so this basically concludes our discussion of exhaustive search attacks, and next we'll talk about more sophisticated attacks on DES.